This section's all about arc length. This is generally everyone's favorite section in this unit because it's simple. We're just figuring out how long the arc is in our curve, a piece of the curve, the length of a piece of a curve. And the way we do it is we divide it up into little lines and find the length of the lines and then let the number of lines that we divided into approach infinity. You can see where it's going. It's like a Riemann sum, which we use an integral to compute. So, if the curve is a polygon, it's easy. We know how to find the perimeter of a square or an octagon. We just measure the sides and add them all together. So that's really what we're doing. We're dividing it into little pieces, little straight lines. So we look at the length of one of those little straight lines, and we'll call it the distance from point I minus 1 to point I. So P sub I minus 1 is x sub I minus 1, y sub I minus 1, and point I is x sub I, y sub I, because that's how we number things. So this length here is equal to the square root, the difference between the x's squared and the difference between the y's squared, just the plain old distance formula. So x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. Now the mean value theorem tells us that there is some special number that lives between p sub I and p sub I minus 1, such that the derivative at that point is equal to the slope of the secant line that connects the two endpoints. So I'm going to call that C sub I. You'll often see it called X star sub I, but that's just a lot of stuff. So I'm going to just call it C. So F primed of C sub I is equal to, I'm going to go ahead and write it out as the change in the outputs. So F of X sub I minus F of X sub I minus 1 over X sub I minus X sub I minus 1. Well, F of X sub I and F of X sub I minus 1 are Y sub I and Y sub I minus 1. So I have F primed of C sub I times X sub I minus X sub I minus 1 is equal to Y sub I minus Y sub I minus 1. This is delta X. This is delta Y. So now I'm going to replace this. So let's come on down here. This is equal to delta X sub I squared, and then we have F primed of some other variable that we know lives between there of delta Y, or delta X sub I, because we're replacing delta Y sub I squared with delta X sub I, and now this is squared. So I replaced X sub I minus X sub I minus 1 with delta X sub I. I replaced Y sub I minus y sub I minus 1 with f primed evaluated at that number that's guaranteed to exist by the mean value theorem times delta x, because this is delta x, and that's delta y. So now I have square root of delta x squared times the square root of 1 plus f primed of something that lives between point 1 and point 2, or point I and point I sub I minus 1 squared. So if we look at this limit here, the limit as n approaches infinity, so the number of little subintervals that we divide it into approaches infinity, this becomes an integral, which would be the integral from a to b. And remember, the square root of delta x squared will be our dx, and we have the square root of 1 plus f primed of x squared. And that is our formula for arc length. Integral from one end to the other, square root 1 plus the derivative squared. I won't expect you to replicate this little proof here. It's just to kind of help you remember where it came from. So let's do an example. We want to find the length of the arc of the semi-cubical parabola y squared equals x cubed. So let's write that down. That's important. Y squared. I said y and I wrote x. Y squared equals x cubed. From 1, 1 to 4, 8. So first thing I need is the derivative of y with respect to x. So I need to have a function of x. And from 1, 1 to 4, 8, that means we're above the x-axis. So y is equal to x to the 3/2. The piece below would be y equals the negative of x to the 3/2, because it's on both sides of the x-axis. But we're on the part that lives above. So y primed is equal to 3/2 of x to the 1/2. So y prime squared, and you can do this in as many steps as you want. I'm going to go ahead and write down my formula. The length is equal to the integral from, my x's go from 1 to 4, square root 1 plus, and then I'm going to square 3/2 x to the 1/2 power. You can go ahead and simplify all this before you set up your integral if you prefer. So we're going from 1 to 4, square root of 1 plus 9 over 4 times x. Well, that's not bad. That's something we can use u substitution for. U is 1 plus 9/4 of x. So du is 9/4 of dx. And then u evaluated at 1 would be 1 plus 9/4. So that would be equal to 4 over 4 plus 9 over 4 is 13 over 4. And u evaluated at 4 would be equal to 1 plus 9 over 4 times 4, cancel, cancel, it's 10. So now we have the integral from 9 over 4 to 10 of u to the 1/2 power, and then du over 9/4, which is 4 over 9, add 1 to the exponent, divide by the new exponent, and evaluate from 9 over 4 to 10. 4 over 9 times 2 over 3, I just invert and multiply. I have 10 to the 3/2 minus 9 over 4 to the 3/2. And let's look at the pretty answer. 13 over 4. 9 over 4. So yes, I plugged in 9 over 4 instead of 13. This should be 13 over 4. This should be 13 over 4. And this should be 13 over 4. Oops, right here. 13 over 4 to the 3/2 power. And with some simplifying, I ended up with 1 over 27. I found the least common denominator here. If you left it just like this, it would be fine. You might want to go ahead and multiply, get 8 over 27, but even if you left it just like that, I would be fine with that answer. That's perfect. Now, the nice thing about arc length is it doesn't matter if you integrate with respect to x or with respect to y. You can do whatever is easiest. So, arc length works exactly the same if you do it the other way. So if I wanted to do this problem, and instead of integrating with respect to x, I wanted to integrate with respect to y, I could just rewrite this as x is equal to y to the 2/3 power, then dx dy is equal to 2/3 y to the minus 1/3 power. So the length would be equal to the integral from y equals 1 to y equals 8 this time, square root of 1 plus 2/3 y to the negative 1/3 squared dy, which we're going from 1 to 8. And now we have the square root of 1 plus, and I would have 4 on top of 9y to the 2/3 power. Because when we square the 1/3, we multiply the exponents. That's not as friendly to integrate, but I'm going to plug it into my calculator and see that I will get the same answer. Okay, I plugged the integral in. You know, your calculator makes you use x's, even though I have it written down with y's. That's okay. And then I just plugged in the negative 13 times the square root of 13 plus 80 square root of 10 divided by 27 into my other calculator. And it's exactly 7.6337, 7.6337. So it doesn't matter which way you do it. If you're asked for an exact answer, I would definitely do this one with respect to x instead of respect to y. Let's look at example 2. This time we have y squared equals x, and we're going from 0, 0 to 1, 1. So x equals y squared dx dy is equal to 2y. So we have length is equal to the integral from, our y's go from 0 to 1, x's went from 0 to 1 too. So 0 to 1 square root of 1 plus 2y squared dy. Now this one's going to require a little more work. This one requires trig substitution because we have a sum of two squares in the middle there. So I'm not going to go through all the steps. You can if you want to. Trig sub and integration by parts to get your exact answer on that one. If I gave you that one on test day, I'd let you plug it in the calculator. Find the exact length of this curve. So that means I want you to use whatever integration techniques are necessary to do this one by hand. And we'll go through it in a minute. Give it a try. How did it go? This one requires some tricky algebra, so we're going to go through it in detail. So first thing I did was I just rewrote this as 1/4 times y to the minus 2 power, just to make it really easy to take the derivative. And this one I did simplify instead of rewriting the integral over and over again. So 4 fell down, subtract 1 from the exponent, negative 2 fell down, subtract 1 from the exponent, and then I simplified that. Then I squared it, and I just wrote down the first term squared, 2 times the first term times the last term, and I put the minus sign in there because the second term is negative, plus the last term squared. Then I simplified that. So I ended up with y to the 6th over 4 minus a half plus 1 over 4 y to the 6th. Then I added 1 to it. And when I add 1 to it, I have 1 minus a half. That gives me plus 1/2. So that just happens to be the square of y cubed over 2 plus 1 over 2 y cubed. That way, when I plug it underneath that radical, the squared and the square root just undo one another, and it becomes easy. I just had to add 1 to the exponent, divide by the new exponent, add and divide, plug stuff in. I had to get some common denominators, which I did down there, and I got an exact answer. So you're going to see that happen fairly often with these problems when you're asked for exact answers. Let's try practice number 2. Find the exact length of this curve. So give it a try and we'll meet back here and compare. So we kind of had a similar thing go on here with our x minus something squared becoming x plus something squared. Let's go through. First thing I did was isolate my y. I chose to do this one integrating with respect to x because it's a whole lot easier to rewrite this as a function of y in terms of x as opposed to a function of x in terms of y. So first I rewrote it. I took the derivative, simplified it, squared it, simplified the square. So exponent fell down, subtract 1 from the exponent, don't forget the chain rule. Distribute, divide into pieces, and then I canceled the 4's. I added 1. I got a common denominator. You didn't have to do that. You might have just recognized that this was x minus 1/2, or x over 4 minus 1/2 squared, x minus 2 over 2 in parentheses squared. You might have recognized that. I didn't. So I got a common denominator and rewrote it, and then this jumped out at me as being a perfect square trinomial because I have a square here, 2 times the first term times the last term, etc. So then I just threw that underneath the radical, took the square root of something squared, and then it was easy to integrate, and I did a bunch of arithmetic, and there you go. So, easiest section, I think, in this unit. Just memorize the formula, do it whichever way is easier. Remember, if you're integrating with respect to x, you get your limits of integration from the x coordinates. If you're integrating with respect to y, get your limits of integration from the y coordinates. Often your problems are just going to give you the end points of the intervals over which you're integrating or finding the length.